Welcome to the course on game theory in the autumn term 2020 at the University Mannheim. This is the first video of week 8. In this video I want to prove theorem 514. We have seen this already in the last video. It is due to Reinhard Selten from 1975. He got the Nobel Prize together with Nash and Harsani in 1994 for their work on Nash equilibria and refinements like this one. So Selten considered a finite extensive game without chance moves and with perfect information, and he studied the backward induction, which gives certain strategy combinations of the associated game in normal form, and he characterized these strategy combinations. It turns out that they are precisely all the subgame perfect equilibria. In general, quite often we have more than one because the algorithm is not exactly a unique algorithm. There are some choices involved, and different choices give different strategy combinations in general. But the result is still fine. Taking into account all possible choices, we get precisely all the subgame perfect equilibria. So, but this notion is non-trivial. What is a subgame perfect equilibrium? It was written here. So, the extensive game in any subgame induces an associate game in normal form. We have seen the definition. And any subgame is also an extensive game. It induces also an associate game in normal form. And now a strategy combination of the associated game for the full game induces also a strategy combination for any subgame. So in the strategy combination of the full game is called subgame perfect equilibrium if for any subgame the induced strategy combination is the Nash equilibrium of this associated game in normal form. So this concept is rather difficult, it's rather complicated, and that's the reason why the proof is also complicated. So the proof necessarily must unwind this definition and go through this definition, and because of that it's complicated. So the proof does not really present some surprising idea or some trick. It's just that the statement itself is complicated because the objects subgame perfect equilibria are complicated, and the proof has to go through these definitions, and therefore it is also not so easy. So yes, in the first step of the algorithm, we had a non-final play alpha with maximal length had been chosen, and we had considered the restricted game, where this alpha becomes a final play, and it also considered the very small subgame which starts at this play alpha. So in the old game can be considered as a concatenation of the restricted game, where alpha is a final play, and the subgame which starts at alpha. I will not define now the notion concatenation. I think it's from the picture it should be clear. So here you see the picture. So the game which starts at alpha is very small. It has just length 1. All the final plays there have length 1. And the game which I obtain if I make alpha into a final play, it's called gamma tilde, and now I call it restricted game. So, and here you see clearly that the whole game is somehow, I call it concatenation of the restricted game and the small subgame which starts at alpha. So this small subgame is a game of length 1. All the final plays they have just consists just of one sequence. And for any player except the player whose turn it is to play after alpha, his strategy combinations for the full game is equal to his set of strategies for the restricted game. It's clear from the picture. For the player P of alpha, whose turn is it to play after alpha, it's a bit different. His set of strategies can be decomposed as a product of his set of strategies for the restricted game and the set of possible moves after the play alpha. So then we can even write any such strategy as a pair, a restricted strategy for the restricted game, and one possible move after the play alpha. So now let's look at the following three conditions or properties. Property 5.1, a strategy combination of the full game is a subgame perfect equilibrium. Property 5.2, a strategy combination is tilde of the restricted game is a subgame perfect equilibrium of the restricted game. Property 5.3, a move S P of alpha after the play alpha satisfies that within the set of all values for all possible moves Z after alpha, the value for this move is maximal. So now I have a precise claim. I claim that the condition 5.1 is equivalent to the conditions 5.2 and 5.3. So I claim that condition 5.1 holds for a strategy combination S if and only if the restricted strategy combination S tilde satisfies F5.2 and the move S P of alpha after the play alpha satisfies property 5.3. So S tilde as well as this move are induced from S. And on the other hand, together they also imply S. We have seen this here. So for the player P of alpha, his restricted strategy and his move after alpha together make up his full strategy. So, and now I claim that this claim is sufficient. When we have proved this claim, then we can conclude that both parts A and B of the theorem are true, as follows. So both parts A and part B follow from this claim by backward induction. So induction hypothesis, we suppose that the parts A and B of theorem 514 are valid for the restricted game gamma tilde. That means we claim that the second step until the last step of the backward induction gives, taking into account all possible choices, exactly all subgame perfect equilibria of gamma tilde. This is really the statement of the theorem now applied to the restricted game gamma tilde. So, and this induction hypothesis and claim 1 now give us what we want. So if we have apply backward induction, then the induction hypothesis says that the restricted strategy combination S tilde gives subgame perfect equilibria of gamma tilde. And the first step of backward induction, of course, gives us a move Z after alpha, which is optimal for player S, for the player P of alpha. So this is property 5.3, and the property of S tilde was property 5.2. And because they imply 5.1, that means that the resulting strategy combination from the full backward induction satisfies 5.1. So it is a subgame perfect equilibrium of gamma. So this gives part A. And vice versa, if we have some subgame perfect equilibrium of the full game in part B of the theorem, then it satisfies 5.1, and then S tilde satisfies 5.2, and the induced move after alpha satisfies 5.3. And that, yeah, but then we know that S tilde is a result of the backward induction for the steps 2 to the last step, and this move after alpha is a result of the first step of the backward induction. So we get this pair of S tilde and this move as a result of backward induction, so we get S as a result of backward induction. So these were many words, but it's really, think about it yourself. The theorem 514, parts A and B, follow from this claim 1 together with induction, namely backward induction. So it rests now to prove claim 1. But for that now we have to go into the definitions of subgame perfect equilibria. So here now I consider conditions 5 for beta and 5 beta. So now I have to unwind the definition of a subgame perfect equilibrium. So let us look at some non-final play beta for the full game. Then a given strategy combination for the full game induces the strategy combination S upper index beta for this subgame which starts at beta. And this induced strategy combination is a, now property 5 for beta says this induced strategy combination is a Nash equilibrium of the game in normal form which is associated to gamma beta. And similarly, if we start with some non-final play for the restricted game, then and look at the strategy combination for the full game, then the induced strategy combination for the subgame which starts at beta of the restricted game is a Nash equilibrium of the game in normal form which is associated to the restricted game. This is property 5 beta. So again, these are just two conditions. I don't claim that they are true or wrong, just two conditions. And now we of course we recall that the non-final plays of the full game are the final plays of the restricted game, non-final plays of the restricted game together with the play alpha, which is non-final in the full game but final in the restricted game. And now the definition of a subgame perfect equilibrium says that a strategy combination satisfies F5-1, so it is a subgame perfect equilibrium of the full game if and only if for any non-final play beta of the full game the corresponding property 5 for beta holds. That means that the corresponding strategy combination is a Nash equilibrium of the associated game in normal form. This is just the definition of subgame perfect equilibrium. And similarly for the restricted game, the restricted strategy combination S tilde is a subgame perfect equilibrium of the restricted game gamma tilde, which is property 5-2, if and only if for any non-final play in the restricted game, the induced strategy combination of the subgame S gamma tilde of the subgame, maybe gamma tilde beta, is a Nash equilibrium of this subgame. This is property 5 beta. So these are just two definitions. And now I say that claim 1 follows from this equivalence or this explicit way to write the subgame perfect equilibria together with the following claim 2. Claim 2 has 3 parts. Here it is. So we have to study now these conditions 5 for beta, 5 beta, and again 5-3. So you recall that claim 1 says 5-1 is equivalent to 5-2 and 5-3. And 5-1 is now the bunch of all the conditions 5 for beta. 5-2 is the bunch of all the conditions 5 beta. So now we have to compare on the one side the bunch of all conditions 5 for beta, and on the other side the bunch of all conditions 5 beta together with 5-3. And claim 2 does this. It makes this comparison. It's very precise. So if beta is a non-final play of the restricted game, and if it is not coming before alpha, then 5 for beta and 5 for beta equivalent. This is part A. If beta is a non-final play of the restricted game and it comes before alpha, then we need 5-3. If 5-3 holds additionally, then again 5 for beta is equivalent to 5 beta. And if, in the third case, beta is equal to alpha, then 5 for beta is equivalent to 5-3. So maybe I first show the next picture, which shows gives an idea of this separation into several cases. So here you see the cases in A and B. Here the left picture is for part A. There beta does not come before alpha. So then the subgame gamma beta and the subgame gamma alpha are disjoint. And yeah, then it is the claim of the part A of the claim is rather clear. 4 beta is equivalent to 5 beta because the subgame gamma beta is equal to the subgame gamma tilde of beta. Because alpha is not part of the game gamma beta, one doesn't lose anything if one makes alpha into a final play. So the subgame gamma beta doesn't see alpha and what is happening there. Therefore, gamma beta is equal to gamma tilde beta, and therefore the strategy and strategy combinations they are the same, and therefore the induced strategy combination is a Nash equilibrium for the subgame of the full game, if and only if it's a Nash equilibrium for the subgame of the restricted game, because these games are just the same. So this shows part A already. 5 beta is equivalent to 5 beta in this situation. In part B, here beta comes before alpha, and we see here the relation. So gamma beta, the subgame gamma beta, contains now the non-final play alpha, and it contains now the restricted subgame gamma tilde beta. So in this part B, I still have to do some work. This is non-trivial. For part C, I don't have a picture, but now let's discuss first part C. Here I'm in part C here. So in this case, gamma beta is equal to gamma alpha, and this is a game of length 1. And there's only one player, there's only one non-final play. And the associated game in normal form consists just of the moves which she can do and the utility values which she obtains after each of these moves. And then it's clear that an optimal move is just a Nash equilibrium. So if you have a one-player game, a Nash equilibrium is a rather trivial thing. Nash equilibrium is just an optimal strategy of this player. And here the strategies are precisely the moves which are possible after play alpha, and the optimal moves are the moves which are Nash equilibria and which satisfy 5-3. Therefore, in this part C, also 5 beta is equivalent to 5-3. So the least trivial case is the case B, where the non-final play beta comes before the play alpha. In that case, we can somehow forget everything which comes before beta, so we can restrict to the situation where beta is equal to the start play n. So we can then restrict to this situation, and then we can reformulate the claim to B in the following way as claim 3. So and then this reduces to this claim 3, which comes now. So now we can suppose that the game gamma beta is equal to the full game gamma, and that beta is the starting play n. So now we look at any strategy combination of this full game. We can write it as a tuple strategy combination of the restricted game and strategy combination of the small subgame which starts at alpha. So then the whole set of strategy combinations can also be written as a product of the strategy combination of the restricted game times the set of moves after alpha. And in claim 3 now we again suppose that 5-3 holds, and then claim 3 says that S is a Nash equilibrium of the full game if and only if it's the restricted strategy combination S tilde is the Nash equilibrium of the restricted game. So this, I scroll back, this is precisely what claim 2b says in the case of this subgame which starts at beta. 5-4 beta means Nash equilibrium of the full game, gamma beta, and 5-5 beta means Nash equilibrium of the restricted game, gamma tilde beta. Here I show also again the picture. So here in the picture we just forget everything which is above beta in claim 3. So now what we still, the only thing which we have to do is to prove this claim 3, but there is still some work to do. So let's still unbind the definition. What does it mean that S is a Nash equilibrium of the full game, and what does it mean that S tilde is a Nash equilibrium of the restricted game? So S to be a Nash equilibrium of the full game means for any player I that his utility function restricted to his set of strategies where S minus I is fixed has a maximum at this strategy Si. So his strategy Si must be a best answer to the strategy combination S minus I of the other players. That is the usual definition of a Nash equilibrium. And similarly, for any player in the restricted game, the restricted strategy combination is a Nash equilibrium if the utility function where S tilde minus I is fixed has the maximum at the strategy S tilde I of player I. This is again essentially the definition of the Nash equilibrium. So we have to work with this explicit description. Now, first suppose that the player I is not the player whose P of alpha, whose turn it is to play after the play alpha. In that case, then the set of strategies of player I of the full game is equal to the set of strategies of the restricted game. And then also the restricted strategy is equal to the full strategy of this player. And then also the two utility functions coincide. So for a player I not equal to the special player whose turn is to play after alpha, the two conditions are just equivalent. So Si is the best reply if and only if S tilde I is the best reply, because we have the same sets of strategies and some of the same values there. So this is easy. The difficult case is the case of the player P of alpha. Now let's consider the player P of alpha, I equal P of alpha. Then his set of strategies in the full game is a product of the set of strategies of the restricted game times the moves, his moves, possible moves after the play alpha. And with this identification of the set Si of all his strategies, the restricted utility function U tilde I can be identified with the restriction of the full utility function on Si to this slice Si tilde times the specially chosen strategy after the play alpha. So therefore the second condition follows from the first condition. If Si is an optimal best reply to the S minus I, then also S tilde I is the best reply to S minus I in the restricted game. Because Si is the maximum for the full set of strategies, big Si, and then S tilde I is also a maximum for this function on the subset, of course. So in order to see that also the first condition follows from the second condition, one has to show that the restriction of the utility function on the full set Si, so the full product S tilde I times Z of alpha times moves after alpha to this slice where the move after alpha is fixed, does not change the maximum value. So the restriction should still have the same maximum value as before, because then also this strategy combination is also a Nash equilibrium of the full game. So now suppose that we have some Nash equilibrium, some best reply T upper I, some strategy of player I, T upper I, which is the best reply to S minus I, which I can also decompose as T tilde I and Ti of I after alpha. So T tilde I is a restriction to the restricted game gamma tilde of his strategy, and Ti of alpha is the move done after alpha. If T tilde I does not lead to the play alpha, then the choice of the move after alpha is irrelevant. Then the value of this full strategy Ti together with this minus I is independent of the choice of this move after alpha. So then we can replace the Ti of alpha also by Si of alpha. And we get the same maximum value. And then T tilde I Si of alpha is also a Nash equilibrium. And then we have the same maximum value on the restricted function. And that's what we need. So the other case is then if the restricted strategy T tilde I together with the combination of the other players leads to the play alpha, then the utility value of the full strategy of the Nash strategy of Ti of player I and the combination of the other players is equal to the utility value of the final move Ti of alpha done after alpha for the player I. But this cannot be better, cannot be larger than the utility of the final move Si of alpha, because Si of alpha satisfies phi 3. We had chosen Si of alpha in the first of backward induction as an optimal move. So in Ti of alpha then cannot give a better utility than Si of alpha. Therefore, the utilities cannot be different. We can again replace Ti of alpha by Si of alpha, and we can again get that the Nash equilibrium of the restricted game has the same value as the Nash equilibrium of the full game. So the maximum value of this function does not change if one restricts it from the full set of strategies of player I to this slice, where the move after alpha is fixed. So this now ends the long proof. Therefore, the two conditions about Nash equilibrium for the player I who is playing after alpha are equivalent. And this then proves the claim 3, and this proves the claim 2b, and by backward induction this proves claim 1, and this proves then the whole theorem 514. So this is the end of this video. In the next video I will discuss this result and come to examples.